You'd think the hardest part of launching a rocket is, actually launching the rocket. But surprisingly, that's not always the case. In many ways, fueling it is an engineering nightmare all on its own. The launch itself only lasts a few minutes, yet loading hundreds, or in Starship's case, thousands, of tons of propellant takes hours. And it's not exactly a relaxing process. You're dealing with fuels that are incredibly flammable, liquids so cold they can freeze almost anything they touch, and pressures high enough that one small mistake could turn a multi-billion-dollar rocket into the world's most expensive fireworks show. So today, we're taking a look at the biggest rocket currently flying, SpaceX's Starship. We'll break down how SpaceX manages the challenge of fueling something this enormous, what actually happens inside the vehicle during those final moments before liftoff, and some of the clever engineering solutions they've come up with to make the whole process faster, safer, and more reliable than ever before. So, let's get into it. What exactly is rocket fuel? But first, what exactly is rocket fuel anyway? At its core, fuel is simply a substance that releases energy when it reacts with oxygen. In a rocket engine, that energy is converted into the thrust needed to escape Earth's gravity. Unlike a car engine that pulls oxygen from the atmosphere, rockets have to carry both their fuel and an oxidizer because, well, space isn't exactly known for its breathable air. Inside the engine, the fuel and oxidizer are pumped into a combustion chamber where they ignite, producing extremely hot, high-pressure gas. That gas rushes out through the engine nozzle at incredible speed. Thanks to Newton's third law, for every action, there's an equal and opposite reaction. The exhaust is blasted downward, and the rocket is pushed upward. It's surprisingly simple in theory. In practice, it's one of the most demanding engineering challenges humans have ever attempted. There are two main ways to do this: solid and liquid propellants. Solid rockets are simple, reliable, and can sit ready for years, but once they're lit, they're committed. There's no throttle, no restart, and definitely no, oops, let's try that again. Liquid-fueled rockets, on the other hand, are far more complicated. They require pumps, valves, plumbing, and carefully insulated tanks, but they give engineers something every rocket designer dreams of: control. They can throttle the engines, shut them down, restart them, and fine-tune performance throughout the flight. That's exactly why modern reusable rockets like SpaceX's Starship rely on liquid methane and liquid oxygen, even if fueling them sometimes feels less like filling a gas tank and more like performing surgery on a skyscraper. Now, Starship doesn't just run on liquid methane and liquid oxygen. It runs on supercooled liquid methane and liquid oxygen. Why bother making the propellant even colder? Simple. Cold liquids are denser. Think about filling a box with marbles. If you swap the big marbles for slightly smaller ones, suddenly you can cram a lot more into exactly the same box. Liquid oxygen behaves in a surprisingly similar way. Cool it down far enough, and it shrinks just a little. That tiny shrinkage lets SpaceX squeeze roughly 14% more oxygen into the exact same tank. That might not sound like much, but in rocket terms, it's basically free performance. More propellant means longer engine burns, more payload, and more overall capability, all without making Starship any larger. It's like discovering your backpack secretly has another compartment, except your backpack weighs thousands of tons and occasionally flies to space. So, how does SpaceX cool millions of kilograms of oxygen? You'd think SpaceX would need some enormous industrial freezer to cool millions of kilograms of oxygen. Nope, they use something even colder: liquid nitrogen. Liquid nitrogen boils at around -196 degrees Celsius, making it significantly colder than liquid oxygen. At Starbase, the liquid oxygen flows through massive heat exchangers, often called subchillers, that are surrounded by liquid nitrogen. Heat naturally flows from the warmer oxygen into the colder nitrogen, chilling the oxygen even further before it heads into Starship. The nitrogen doesn't stick around afterward. As it absorbs heat, it boils into gas and vents into the air. That's why, during fueling, Starbase often looks like it's filming the world's most expensive haunted house fog machine. Those giant white clouds are mostly nitrogen gas mixed with water vapor condensing out of the humid Texas air. Of course, using propellant that's cold enough to make Antarctica seem tropical comes with a few challenges. One of the biggest is that fueling too quickly can actually damage the rocket. Imagine pouring boiling water into an ice-cold glass. There's a decent chance you'll hear an expensive little crack. Metal behaves in a similar way. Raptor engines eventually operate at around 1,800 degrees Celsius, but before launch, they're sitting outside at ordinary temperatures. Suddenly blasting them with liquid oxygen at around minus 183 degrees Celsius and liquid methane that's even colder would make different parts of the metal contract at different rates. That's a great way to create tiny cracks in hardware that absolutely cannot afford to have tiny cracks. Then there is also cavitation. When cryogenic liquid touches warm engine hardware, some of it flashes into gas almost instantly. If those gas bubbles form inside the turbopumps, which are already spinning at ridiculous speeds, they can disrupt the propellant flow and even damage the pumps themselves. Imagine trying to drink a milkshake through a straw that's randomly filling with air bubbles every second. It doesn't work very well. Now replace the milkshake with liquid oxygen and the straw with a machine producing tens of thousands of horsepower, and you've got the idea. That's why SpaceX performs what's known as a chill down before full fueling begins. Instead of opening the valves all at once, engineers slowly bleed small amounts of liquid oxygen and methane through the engine lines, valves, and turbopumps. The cryogenic propellant gently absorbs the heat from the metal hardware, carrying it away as harmless vented gas until everything reaches nearly the same freezing temperature. Only once the entire system is properly chilled do they start pumping propellant at full speed. There's another surprisingly tricky challenge. Liquid oxygen and liquid methane have very similar temperature limits, leaving SpaceX with almost no room for error. Even stranger, oxygen freezes at a higher temperature than methane boils, creating an awkward balancing act. This is especially important because the two propellants are separated by a common dome, a single metal wall. If the oxygen gets too cold, it can draw enough heat through that wall for the methane on the other side to start freezing. And frozen methane is the last thing you want. It can restrict propellant flow and cause problems for the Raptor engines during startup. That's why, during the rapid fill phase just before launch, SpaceX carefully manages the temperature of both propellants instead of simply making them as cold as possible. The goal is to keep the oxygen dense while making sure the methane stays perfectly liquid. It's one of those problems that sounds tiny on paper, but can make a very expensive rocket have a very bad day. Okay, now you know why fueling the biggest rocket ever built is almost its own engineering project. So here's what actually happens before every Starship launch. It all starts at Starbase's tank farm, which is basically the world's most overqualified gas station. Huge insulated tanks store liquid oxygen and liquid methane at ridiculously cold temperatures, waiting for launch day. Once the propellant is ready, the rocket itself has to be assembled. The Starship upper stage is lifted by the giant Mechazilla tower and carefully stacked on top of the super heavy booster. It's basically the most stressful game of crane operation ever invented. Next come the quick disconnects, or QDs. Think of them as incredibly sophisticated fuel hoses. Except instead of filling your car with gasoline, they're pumping thousands of tons of cryogenic propellant while also supplying electrical power, data connections, and other services. Then, just before launch, they have to disconnect and swing completely out of the way in just a few seconds. Higher up on the tower is the Ship Quick Disconnect. A massive arm reaches out to connect with Starship itself, loads both liquid methane and liquid oxygen, then rotates safely away before liftoff. Now everything starts happening really fast. Starship countdowns usually begin fueling only about 35 to 40 minutes before launch. That's incredibly quick for a rocket this size. The ship typically starts taking on liquid oxygen first, followed by the booster loading both oxygen and methane just a few minutes later. Thousands of tons of propellant race through insulated pipes, giant valves, and manifolds at astonishing flow rates, while everything is kept cold enough to stay liquid. As the tanks fill, you'll see those giant white clouds pouring off the rocket. It looks dramatic, but as we discussed earlier, most of that is perfectly normal. Some propellant naturally boils as tiny amounts of heat leak in, so the system continuously vents excess gas to keep tank pressures under control. Wherever possible, SpaceX even captures the methane boil-off instead of simply letting it escape. A little later in the countdown comes engine chill. Before the Raptors can fire, super cold propellant is circulated through the engines to cool the turbopumps. If everything behaves itself, the tanks are topped off, pressures are stabilized, the quick disconnects swing away, and the rocket is officially ready to fly. Before launch day, SpaceX usually practices this entire sequence with a wet dress rehearsal, loading both stages with real propellant and running the countdown almost all the way to engine ignition. And of course, launch day almost never goes exactly as planned first try. Maybe the weather refuses to cooperate. Maybe a sensor reports something weird. Maybe an engineer notices one tiny number that's slightly outside its expected range. Whatever the reason, sometimes the countdown has to stop. So what now? Once the rocket is full, the clock is still ticking. The methane is just sitting there. The oxygen is still unbelievably cold. Meanwhile, heat is constantly sneaking through the stainless steel tanks. Very slowly, the temperature balance begins to change. Wait long enough, and the methane can actually start freezing. That's definitely not on SpaceX's launch checklist. So they can't simply pause the countdown forever and hope everything works itself out. If the delay drags on too long, there's really only one option. Drain the rocket, let the systems warm back up, refill everything, and try another day again. It's frustrating. It's expensive. Everyone watching the live stream groans in unison. But hey, that's just another day when you're trying to launch one of the biggest rockets in the world. Even though fueling Starship hasn't magically become easier, SpaceX has gotten much better at it. That's kind of the company's entire philosophy. Find the bottleneck, fix it. Find the next bottleneck, fix that too. Repeat until your engineers start asking what sleep feels like. And it's not just the rocket that's evolving. A huge part of the progress is happening on the ground. Take Launch Pad 2 at Starbase. At first glance, it just looks like another launch pad. In reality, it's more like a giant machine built solely to prepare another giant machine. The propellant farm has been expanded with much larger storage tanks and far more pumps, allowing Starship to be fueled significantly faster than before. Considering the rocket drinks over 2 million liters of cryogenic propellant every launch, faster fueling isn't just convenient. It's the difference between launching often and spending your entire week waiting for tanks to fill. The launch tower has received plenty of upgrades as well. The Ship Quick Disconnect Arm, the massive arm that fuels the upper stage, has been strengthened, repackaged, and redesigned to swing much farther away before liftoff. That extra clearance might not sound exciting, but when a 120-meter-tall rocket is leaving the pad surrounded by fire, a little farther away suddenly becomes a fantastic engineering decision. Down below, the launch mount has practically been rebuilt from the ground up. The hold-down clamps have been redesigned to spread the enormous launch loads more evenly while improving reliability during liftoff. Inside the mount, engineers added an entirely new flame diverter and flame deflector system that's designed to survive launch without constantly being chewed apart by 33 Raptor engines. Less damage after every flight means less refurbishment, which means faster turnaround. And if rapid reuse is the goal, every hour you don't spend repairing the pad is a win. Even the plumbing got an upgrade. The booster quick disconnects have been moved to the opposite side of the launch mount and split into completely separate methane and oxygen connections. The maze of valves, filters, and fill systems has also been relocated into a reinforced bunker beside the pad, where the methane and oxygen equipment are isolated in separate rooms for safety. Put all these changes together, and you start seeing the bigger picture. None of these upgrades exist just to shave a few minutes off fueling. They're laying the foundation for what SpaceX actually wants: rapid reusability, orbital propellant transfer, regular Starlink deployments, and eventually sending cargo and people to the Moon and Mars. You don't get there with one revolutionary breakthrough. You get there by making hundreds of small improvements that add up over time. And believe it or not, they're not stopping there. Right now, every Starship launch requires roughly 630,000 gallons of liquid methane. Today, that fuel largely arrives by truck, lots of trucks. Imagine trying to supply an airport by having hundreds of fuel tankers drive in one after another. It works, but it's hardly a recipe for launching rockets every other day. So SpaceX's solution is very SpaceX. Instead of ordering more trucks, they're building a pipeline. The company plans to construct an 8-mile, or roughly 13-kilometer, natural gas pipeline nicknamed Starpipe that will connect directly to Starbase. The idea is simple: deliver massive amounts of methane continuously without relying on endless convoys of tanker trucks. It's expected to enter service as Starship's flight rate continues to ramp up. Because let's be honest, If your long-term goal is hundreds, or eventually thousands, of launches every year, your logistics can't look like a Costco parking lot. But Starpipe may only be the beginning. For years, SpaceX has talked about producing more of its own propellant, building its own processing facilities, and even exploring the possibility of drilling for its own natural gas in Texas. That's a pretty unusual direction for a rocket company. Most aerospace firms buy fuel from energy companies. SpaceX seems to be asking, what if we just became part energy company too? It's an ambitious strategy, and not everyone thinks it'll be easy. Building rockets is one thing. Extracting and processing natural gas is an entirely different industry with its own challenges and expertise. But if history has taught us anything, it's that SpaceX really likes controlling as much of its supply chain as possible. They build their own engines, they build their own spacecraft, they manufacture most of their own hardware. Building the infrastructure that feeds those rockets almost feels inevitable. Because in the end, getting humanity to Mars isn't just about building a bigger rocket. It's about making sure that every part of the system, from the fuel buried underground all the way to the rocket sitting on the launch pad, can operate quickly, reliably, and over again. After all, you can't build an interplanetary transportation system if you're still stuck waiting in line for the fuel truck.